Hello, everyone. My name is Lingshu Wang. I'm from Oak Ridge National Laboratory. It's my great honor to virtually present my work here. The title of this presentation is a novel high energy density mobile sorption-based thermal battery for low-grid thermal energy storage. Here is the contents of this presentation. The first is the introduction. The second part is the experimental apparatus introduction, and then followed by the experimental results and the discussion. And the next is the parametric study of the performance of the MSTB. And last is the conclusions. Now let's start the introduction part. So we know that the fossil energy consumption is rapidly increasing in the past decades in the world, and it released huge greenhouse gas emissions and caused the global warming problems. And a large part of the fossil energy is consumed for power generation. In the US, the buildings consumes about 75% electricities, of which 40 to 70% of the energy consumed in buildings is for the thermal loads, for example, for the heating, cooling, and air conditioning. So how to reduce the fossil energy consumption? We can use the low grid or renewable energy sources. For example, the low temperature geothermal energy is very abundant in the US, and the waste heat recovered from the vehicles and power plants also abundant. But there are some problems using this low grid heat. The first problem is that this low grid thermal supply usually are far away from the population centers. So it needed to be transported from the heat source site to the building site. But the energy density of this low grid heat is too low to justify the transportation cost. And the second problem is that the building exists the peak and valley demand, but this demand is not easily be matched with the low grid heat. So to solve these problems and to effectively store and transport low temperature thermal energy, so we can use the thermal energy storage technology, especially with the high energy density. The existing thermal energy storage technology includes the sensible thermal energy storage, the latent thermal energy storage, like the PCM, and the sorption thermal energy storage. But there are some disadvantages of this existing technology. Includes the low energy storage density, significant heat loss, insufficient charge and discharge rate. To solve these problems, we proposed a new concept, the mobile sorption-based thermal battery. So this figure shows the schematic of this system. It includes three parts. The left is the heat source site. The middle is the transportation part, and the right side is the building site. So in the heat source site, the low grid heat can be used to generate the concentrated salt solution and stored in the form of the salt crystals. And then the crystals can be transported to the building site to release the stored energy to the buildings by using the air dehumidification or air cooling methods. And there are a few advantages using the MSTB. For example, it has very high energy density. The theoretical energy density is above 900 kilojoule per kilogram, which is about 40 times higher than the chilled water. It also can use the low temperature to generate the hydrate crystals. And it also has various applications for example, the cooling, heating, and air dehumidification. It can be used also used for the seasonal storage without any heat loss. However, the current studies on the MSTB focus on the simulation research. There is the lack of the experimental verification, especially for a prototype. And the crystal formation and the dissolution performance of the MSTB is rarely studied. So in our study, we developed a benchtop prototype MSTB and demonstrate its feasibility with a high energy density. And we will also investigate the influencing factors which affect its performance. So next part is the experimental apparatus introduction for characterizing the MSTB. So this is the schematic of this benchtop prototype. So this prototype has a volume of 4.2 liter, and the crystals occurs by the active cooling inside of the MSTB. The cooling water of the flows along the cooling coil to provide the active cooling. Two filters are designed at the above and bottom of the MSTB to prevent the salt crystals from escaping the tank. And we also designed the internal circulation to enhance the convection performance inside of the MSTB. This figure shows the theoretical thermal energy density of different materials. So we can find that the lithium chloride hydrate crystals has the largest energy storage density when it is used for air dehumidification. So in this study, we used the lithium chloride as the energy storage medium. This is the schematic diagram of the experimental apparatus for characterizing the crystallization and the dissolution performance of the MSTB. We can monitor and control the flow rate, density, temperature of the salt solution during the test. This is the photo of this experimental apparatus. This table shows the specification of the marrying instrument, which including the thermocouples and the flow meters for the cooling water and for the salt solution, and also the density meters of the salt solution. To evaluate the performance of the MSTB, we proposed the evaluation parameters, the energy storage density and the crystal fractions of the charging process, and use the discharge rate to evaluate the performance of the discharging process. And these parameters can be calculated by using these following equations. So we conducted the crystallization test. So this is the test conditions. We used the cooling water at a temperature for around 20 degrees C. This is the test results. So we can find that the crystals formulated around the cooling coil, the tank was almost filled with crystals after 40 minutes. And it was also observed that the crystals were fluffy. So it is helpful for crystal dissolution. This is the test data of the crystallization test. So in the figure A, we can find that the concentration change between the solution leaving MSTB and the entering MSTB. So the concentration of the solution leaving MSTB is lower than the solution entering the MSTB. So it indicates that the solution is diluted after generating the crystals during the test. And the final crystals generated in the MSTB was 34% of the mass percentage. And the corresponding energy storage density was around 903 kilojoule per kilogram. And we also conducted a dissolution test, used the diluted lithium chloride solution after dehumidification to dissolve the crystals stored in the tank. So here is the results of the dissolution test. So we can find that the the lithium chloride hydrate crystal stored in the tank was easily dissolved, and in 16 minutes. This is the test data of this solution test. So we can find that the concentration of the solution leaving MSTB was higher than the solution entering MSTB. So it means that the solution can be concentrated by melting the crystals stored in the tank. And the result also show that the discharge rate can mention at above 1 kilowatt, and the maximum discharge rate was as high as 1.3 kilowatts in this test. We also conducted parametric studies to study the influence factors of the crystallization and this dissolution performance of MSTB. For the crystallization performance, we studied the impacts of the solution flow rates and found that the energy storage density and the crystal fraction decreased with the increasing the solution flow rate. When the solution flow rate was 1.5 gram per second, the maximum energy storage density can be achieved as 980 kilojoule per kilogram, and the corresponding crystal fraction was around 51%. And we also studied the impacts of the cooling water temperature and found that the energy storage density decreased with the cooling water temperature. And when the cooling water temperature was around 30 degrees C, so the solution could also crystallized in the prototype. This temperature can be mentioned by using a cooling tower. We compared the energy storage density achieved in this study with other thermal storage technology, and found that this MSTB can achieve a much higher energy density, which is around 3 times of ice storage and 5.6 times of the phase change material, and about 47 times of the chilled water. So these results show that the MSTB has a significant advantage, and it has promising application potential. So besides the crystallization test performance, we also conducted a parameter study for the dissolution performance. For the impact of the solution flow rates, so we found that a higher solution flow rate results in the higher maximum discharge rate. But as the total energy stored in the tank is limited, so the higher of the solution flow rates, the shorter and less stable of this discharge process. We also found that a higher solution temperature results in the higher maximum discharge rate. So when the temperature of the inlet solution was about 50 degrees C, the maximum discharge rate was about 1.8 kilowatts. And by using the internal solution circulation, we found that 38% increase of the maximum discharge rate can be achieved. So this is also a new design of this system. The reason of this increase is that it can increase the convection inside of the solution convection inside of the MSTB, and to enhance the heat mass transfer performance. To conclude this work, so we experimentally demonstrate the technical feasibility of the MSTB, which has a much higher energy density for transporting the low temperature heat. And we also investigated the influencing factors of this crystallization and the dissolution performance. These findings can be used as the design guide of the MSTB systems. The following work is recommended to move from the proven concept to the practical implementation of the MSTB systems. The first is the optimization of the MSTB design and the system integration. And the second is the develop a full-size prototype and assess the technical feasibility and economic viability of the proposed technology. That's all. Thank you.